Thank you very much. Thanks to the organizers for putting together this conference. This is actually my first week, so I'm looking forward to the workshop too. And thanks for sticking around. A few of us are still in the room. This is the last talk, so I'm the last thing between you and going home, so I keep this hopefully not too long, and also, yeah, keep it light. Okay, so I don't need really this slide for this conference. Dissipation can be useful. It's useful for quantum information applications, quantum simulation, sensing, quantum computation. In particular, it can be useful for a generation of interesting quantum phases of matter. So there's been some recent experiments. More recently, there's been an experiment by the Google. So basically, what they did, they had their setup, and they have some ancillas at the edge, and kind of by resetting those, they could kind of suck out the entropy out of the system, and that way they could realize something close to the grounded state of the Ising model in 1 dimension and also in 2 dimensions. So this comes with advantages. It's an alternative to adiabatic preparation, which it would be limited to short times because you have all kinds of noise. But if you're using noise, then maybe you can fight off, some amount of noise. So that's good. But also it comes with its own problem. So is it scalable? Is it stable? There's been some discussion about this. And you also have some kind of entropy generation. So is quantumness really there, or is it kind of spoiled? So this is so many of the talks in this workshop, they focus on equilibrium, and but actually for this talk, I want to highlight many-body-driven open quantum systems. So the equation looks very similar. You have some Hamiltonian, and you have some distributive dynamics, but detail balance in general is broken, and that would give rise to some non-equilibrium steady state. And the question that we'd like to ask in this talk is that would you still have some quantumness in this non-equilibrium steady state? And different notions of quantumness are different. The notion that quantumness that I'm going to focus in this talk is whether we're going to have a quantum phase transition in a many-body open-driven quantum system. And so I have to be more specific. The kind of assumption that I want to make or not to make is, first, no active error correction. It would be nice to see what are the limits of life without at least active error correction. And then I'm going to consider some generic dynamics. So nothing too specific. So for example, not frustration-free. And if you want, you can also consider some kind of locality. And finally, what I'm looking for is that the most kind of standard notion of phase transition, something that you can identify, a simple order parameter that you can identify and measure. And this is kind of maybe in some sense more conventional, but let's start simple. Okay, so this is the outline of the talk. So for the first half of the talk, I'm actually going to argue that thermalization is an obstruction. It seems like that many of the systems, you're hoping for something quantum perhaps, but they effectively thermalize in some sense. And I have to explain what that means because these systems are really non-equilibrium. And then I present a non-trivial example of a quantum phase transition. So that's recent work. And something that I'm not hoping to get to, but I just want to put this on the slides, is that dissipation can also be a computational resource. This is kind of maybe related to the stuff that Dorit talked about, and I'm just putting there just to inspire maybe some discussions. And maybe, who knows, maybe I get to like the last 2 minutes of the talk. Okay, so let's start, if you want, with an Ising model of open-driven systems. This morning we also heard about the Ising model. My Ising model is kind of another kind of generic model that you can imagine in this context. So the Hamiltonian is just the Ising Hamiltonian that we know and love. And dissipation is something like this. So you have a spin up, which can decay to a spin down at some rate gamma. And the good thing about this Ising model is that dissipation also preserves the Ising symmetry. So that makes it actually easier to talk like the same language of symmetry breaking phase transition. We can still use the same language. And we can ask if we can have a symmetry breaking phase transition in this system. Oh, by the way, if you want to interrupt and ask a question, please do. So The question is, before I pose the question, so if the system orders, then you would expect something like this. So it spins with a line in one direction or the other. I'm just showing you one, but that's basically the question that we ask. And also the question is whether that's actually a quantum phase or phase transition. Okay, and one thing I want to emphasize is that in the sort of transfer field Ising model, without any dissipation, the transfer field is actually what frustrates ordering, so that adds some quantum fluctuations. When you have dissipation, dissipation also has a similar rule, right? So the Ising interaction has to fight against both the transfer field and also dissipation to, to perhaps, give rise to some kind of order. Okay, so you might suspect that at least when H is 0, so we have no quantum fluctuations, maybe that's our best bet to get, an order phase. It turns out that's not the case. Actually, this limit of H being 0, that's exactly solvable. We can solve it for any Hamiltonian, and for kind of very general kind of Ising Hamiltonian. It's not completely trivial, but one thing that you can quickly see from this is that if you look at the density matrix, if you project it in the x basis, so you're just interested in kind of observables which are diagonal in the x, it would correspond to kind of an infinite temperature state. That's not a statement about the density matrix, just that's a statement about the density matrix projected in the x basis. And it's very easy to see that. So imagine that I start from this infinite energy, infinite temperature state, which is just in the middle of the spectrum, so the energy is 0. And let's say that we have one decay. So one of the spins here, they just decay to a spin down. It's very easy to see that this state, it just has the same energy. So dissipation seems like when the transverse field is 0, kind of maybe surprisingly, dissipation does not cool down the system away from infinite temperature. So I guess maybe counterintuitively, perhaps we have to consider some transverse field in order to have some non-trivial state. And here you can see actually in the presence of the transverse field, an instance of dissipation would actually decrease the energy, so cool down the system a little bit, because this state would actually make this part of the energy a little more negative, and that little energy, it can balance itself against the Ising model, so perhaps the system can cool down itself sufficiently and you get some order space. But the question is, it cools down the system, but to what exactly, or how much? And okay, the Hamiltonian for the Ising Hamiltonian is actually quite simple. It's exactly solvable in terms of free fermions, and that might be kind of a starting point, but that doesn't seem very promising because dissipation really exposes real bad. So there are two problems. One problem is that you get strings from the Jordan-Wigner. At the level of the Hamiltonian, they cancel each other out, but when it comes to dissipation, specifically for the so-called jump term, they give rise to this kind of a strings. So there's just infinite kind of many-body terms in the Hamiltonian. And actually worse than that, it might not seem obvious why this would be worse, but this is a free model only if you're in a definite parity sector. The problem with dissipation is that dissipation also changes the parity. So parity, to be precise here, the parity is the number of fermions in the system, mod 2. But dissipation can take out an excitation out of the system, so it would actually change the parity and couple the two parity sectors. So there doesn't seem to be a kind of obvious way around this, except that one can actually find an exact solution in the limit that dissipation goes to 0, but this is still non-trivial because we can consider a finite time in units of 1 over gamma, or just infinite time if you're interested in the steady state. So how does this work? The idea is simple. If you're interested in dynamics in the limit of gamma going to 0, the dynamics is mostly unitary, but occasionally interrupted by dissipation. So what it means that if you start from some initial state on your way to get to the steady state, the dynamics for a long time is just unitary dynamics, and for this system, which is just free fermions, it quickly goes to a GG. So this is a generalized Gibbs ensemble, which keeps track of conserved quantities. But dissipation happens, and that's a bad thing. But again, the system quickly, recovers to a GGE, but possibly a different GGE. So in this way, you have an evolution of GGEs. This GG is almost Gaussian, but not quite. You have the sum of the two parities, and dissipation, like I said, it couples the two. And the dynamics is actually non-trivial. So the thing that kind of simplifies things is that the ansatz for kind of the state of the system at any given time is almost Gaussian, but dynamics is actually quite nonlinear because, yeah. And doing these tricks, I don't want to go really into any detail of this, but you can actually get rid of both problems. You can take care of the strings and you can take care of the parity, and you can kind of solve the problem exactly in a sense. So this is what we did, and this is what you see is called a perturbative solution, but really this is exact in the limit of gamma going to 0, and this is comparison against matrix product of state. And here what I'm showing you is the correlation lengths in the system. And the most important thing that I should emphasize is that there is no ordering in one dimension. The correlation length has some features, but nevertheless it always stays finite, so no phase transition. But curiously, there seems to be a peak, a pronounced peak, near the critical point, actually near the ground state critical point. So what is it? Yep. Yeah. Basically, everything I'm talking about is in the steady state. So a phase transition in the steady state, or yeah. And right. So you see a pronounced peak near the ground state phase transition. So it seems like the system is kind of sensitive to criticality. And so we ask the question whether this is kind of tied to the integrability of the Hamiltonian. I mean, the full dynamics, I just have to emphasize that's certainly far from integrable. Dissipation can't exploit that. But could it be that perhaps considering chaotic Hamiltonians would change this? And we observed that at least for this kind of, second order perturbation, kind of ferromagnetic, if anything, making the system more chaotic actually makes it better. So this is the critical point obviously changes when you add more terms to the Hamiltonian. So here I'm just dividing by HC, but as you can see that when I consider larger and larger perturbations, it seems like the peak is kind of approaching the critical point. So what's going on? So we can actually repeat kind of the same line of philosophy that again if I'll come back to this. But at least for the dynamics in the limit that dissipation is weak, and if the system is chaotic, you can apply kind of the same logic, except that instead of going to GGE, you actually go to GE. And then you're interrupted by dissipation, and so on and so forth. And so it kind of seems intriguing that, so we had a lot of talks in this conference about, I guess, thermal states and Gibbs sampling and so on. And it's, we even had some talks about kind of the proof of ETH. But on one hand, we have this kind of belief now, maybe kind of a theorem or something, that the isolated systems, if chaotic, would go to a thermal state. But also we have open-driven systems in the presence of weak dissipation would also have the same fate. So can we establish a more concrete connection here? And it turns out that if you start from this particular initial state for an isolated system, the steady state that you're going to is just identical to the steady state of this open-driven system in the presence of weak dissipation. So this is the part that both of them would go to a thermal state that's kind of given, assuming you believed me. The part that this particular state would go to a thermal state is something that you just have to compute the energy, and you have to show that the energy of this guy is the same as that guy, so that's the only way it can be. Yeah? Yeah, so by saying thermal state, certainly the notion I have in mind, is that the question? Yeah, I'm certainly having a notion of kind of some kind of substance in mind, yeah. But that would apply to things that I would care about, like expectation values, correlation function, things like that. Any other questions? Okay. And so now, once you establish some kind of connection, you can kind of use one half of it to learn something about the other half. And so recently, I forgot the full reference. My apologies. There was a paper a few years back, mostly numerical, that quench dynamics, when you quench to the critical point, you see some features of criticality. And that's for chaotic systems. That's quite counterintuitive, because chaotic systems, when you do the dynamics, why should they care about the critical point at the ground state? But that's an observation here. We don't have great insight into this, why this happens. The only thing we can say is that if this happens here, we kind of see kind of similar features in the context of the open-driven system. Okay, this is all good. This is kind of nice. We have ways to solve certain problems exactly, and we have this kind of understanding. But in the end, what I was really hoping to find here is that phase transition, not just perhaps some sensitivity to criticality, which in its own right is quite interesting, but can we find a phase transition? So yes, if you go to higher dimensions, there would be a phase transition of, let's say, the exact same model to be concrete. But these phase transitions are effectively thermal. So what that means is that now, for this slide, maybe I should emphasize that so far I focus really on the limit of vanishing dissipation. This is a generic statement now about arbitrary dissipation in the system, and the steady state will be very non-equilibrium. So I'm not saying that this state in any sense, certainly in the ETH sense, is thermal. But what I'm saying is that if you look at macroscopic properties, correlation functions, universality, exponents, they would be in many cases thermal. In some cases, not thermal, but also classical, non-equilibrium classical, but not so much quantum. And there are some exceptions. Actually, Hood has some nice work on this from a few years or more than a few years back. If you have colored noise, that would change the story, but follow-up work shows that if you also consider non-linear corrections, things would kind of be a sport. Okay. This concludes the first part of the talk, that many things in life thermalize, even if they're strongly driven. Now the second part of the talk is that can we identify quantum phase transition in a system that's not very fine-tuned or blah, blah, blah. Okay, so for this, let me start with kind of the model of choice for this part of the talk is actually a paradigmatic model called the spin-Boson model. So this is kind of a paradigm of quantum dissipative systems, not quantum-driven dissipative system, nothing driven yet, but this system is kind of, if you're interested in some kind of impurity that sits in some kind of environment, this is a model that has very rich behavior. And this model has been also, some variation of this model has been realized in quantum simulators. So it's natural to think that, things will be also lossy. So this is kind of the part that I'm not showing you. Now I want to consider this as an open-driven system, that you have some, perhaps, Markovian loss on things in, on the bosons in the system. But I'm kind of having this picture that you have some quantum simulator and you have driven that, and maybe you are in some rotating frame, and you also have some kind of loss. So what's the physics here? What's going on? So if you want, you have two layers of dissipation here. One layer is just dissipation in kind of the good old notion of dissipation. You have many degrees of freedom in the environment, and then you have Markovian dissipation to the outside world. Okay, so kind of a characteristic function that says a lot about the behavior of the bath is the spectral function. And in particular, for an ohmic bath, the spectral function is just by definition scales linearly with frequency with some prefactor. Now, depending on what this prefactor is, you can actually have a phase transition. It's called a localization phase transition, I guess one of the localization transitions. Which means the following. If alpha is small enough, nothing too interesting, you have, if you start from, let's say, spin up. You have some dynamics, maybe underdamped, maybe overdamped, but everything will eventually go to 0. But if the coupling to the bath is large enough, and this is sort of the characteristic, this dimensionless quantity that characterizes the strength of the coupling. If this is large enough, in particular, if this is large enough than 1, you're going to this phase that the spin is kind of stuck in one of its eigenstates. So that means although you have some tunneling that can take you in principle between up and down, above the transition, that tunneling is basically inactive, if you want. Okay. Now, there are many ways that we can kind of understand this localization. My favorite way to think about this is kind of this quantum to classical mapping. It actually brings us back to the Ising model. So the way it works is that you have a single spin, you have a bunch of modes. Let's trace them out or integrate them out. This would actually give you an Ising model, but along the time direction. So this is now a kind of a classical spin model that lives in one higher dimension in the spirit of the quantum to classical mapping. And now you have kind of a long-range coupling between these different spins, which for an ohmic path would go like this. So for kind of a time difference, if you want, if the distance r between two spins, the interaction goes like 1 over r squared. And this model actually is known to give rise to a phase transition, actually to a BKT phase transition. And this is one way that you can kind of understand why you would have a phase transition in this system. Okay, what happens at finite temperature? At finite temperature, basically, the range of the interaction is cut off. So this is a 1D classical model. If the interaction has a finite range, there is no phase transition. Okay? So far, so good. Now, let's finally add dissipation. So far, everything I was telling you, nothing was driven. It was, yeah. Now, let's turn on the dissipation. So now the model is something like this. The Hamiltonian is just the same as before, but we consider some kind of Markovian loss on these bosons, and we ask the question is what is the non-equilibrium steady state? Now, you can kind of use the same picture. Things are now getting a little more complicated. This is a non-equilibrium problem, so you can't really go on imaginary time. It has to be real time, and it has to be a closed time contour. But technicalities aside, you'll still get some long-range Ising model. And again, if you have a constant rate dissipation, the range of interaction is cut off by 1 over kappa. So this is, I think, a very concrete example that you can see why dissipation kind of acts as effective temperature. That's, they have the same they lead to the same, morally they lead to the same thing. Okay, but now how about we do things differently? So now let's consider dissipation. I call this, I guess, a structured the dissipation that's proportional to the frequency of the corresponding node. So I'm assuming that the slow modes also die as slowly. So what happens in that case? So what happens is that the long-range interaction is actually there. The coefficient changes and becomes even complex valued. But the more important thing I want to emphasize is that the modulus of the interaction is reduced because of dissipation. So this R here is kind of the constant of proportionality I consider here. So dissipation kind of reduces the effective coupling. But nevertheless, you still have this long-range thing. So maybe there is hope for something more exotic. Could there be a phase transition that perhaps at a larger value of alpha, now that this is effectively reduced? So our first approach was numerics, and also this is nice because I was kind of in the beginning I was discussing kind of 1D systems and local systems, and this seems very non-local. But there's actually a mapping that you can make that kind of maps this model to a spin which is coupled to a bosonic lattice. So this is without dissipation first, and this has been established some years ago. And in the presence of dissipation, the dissipation that we considered is more structured dissipation. Once you translate this into this new transform lattice, you actually have single site loss, but also you have two site loss. So this is, if you want, this could be my starting point. A perfectly local system of a spin coupled to a bosonic lattice. And okay, now with this, equipped with a local one-dimensional system, you can do your MPS. And this is an example that you get a phase transition from dynamics. You initialize the system in the eigenstate of sigma z and let that evolve. If alpha is sufficiently large, and as we expected, it has to be larger than 1, there is, big enough alpha that this is basically freezing. And it seems like that we have a localization transition. Okay, what is the other line that I'm showing here? This is actually the purity of the system. So we also computed the purity of the entire system, the spin and the boson that is coupled to. And it seems like that the localization transition also coincides with some kind of purifying transition. That the system really, the quantum phase transition happens exactly when you have almost perfect purity. So let's understand this. So for the standard spin boson model with no Markovian dissipation, you can actually, so there's such a thing, it's just called adiabatic normalization. And the basic idea is that you can identify the fast frequencies in the bath, you can integrate them out, and now that gives you kind of a normalized tunneling, and then identify kind of the fast degrees of freedom with respect to the new normalized value, and keep doing this. But let me not get into that in more precise terms, but just say that you get some kind of strong normalization because of the coupling to the bath. And basically what happens is that if alpha is large enough, this renormalized tunneling goes to 0. So that's exactly that the tunneling that could possibly take you between these different eigenstates, that's kind of shut down. So the system is frozen. That's the kind of the system at 0 temperature in the ground state. Now, what happens with Markovian dissipation? So here, I mean, at the technical level, things change quite a bit. We no longer talk about the energy. We don't talk about the ground state. The object of interest is a steady state. But you can do some kind of similar analysis, and it turns out that if alpha is larger than some threshold, more precisely 1 plus r squared, just let's remember that r is the kind of the proportionality constant that was in the dissipation. So this characterizes dissipation in the system. The tunneling rate goes to 0. And when tunneling is shut down, even in this system which has Markovian dissipation, you can see that the system has to be pure. Dissipation is acting on the boson, but if there is no delta, you just have a quadratic system of bosons, and so dissipation would just make this kind of, would shift kind of the harmonic oscillator, but otherwise it would take you to a coherent state. So when this is shut off, that's exactly, shut down, this is exactly when you also get a pure state. Hence, the quantum phase transition is a purity transition in this case. Okay, this actually, how much? Still have some time, right? Okay, let me at least summarize. I thought that I would just make it to this part, but this is kind of the summary part, and then I take questions. But if there's a couple of minutes, maybe I can also tell you just a couple of minutes about something else I'm excited about. So yeah, dissipation to quantum phase transition over different systems. In this kind of example that I presented, that's kind of an atypical situation that evades thermalization. It's actually a purifying transition. And so it's interesting to ask if, or how generic this is. So what if we don't have like this spin boson paradigm, but rather we have a spin chain, maybe in 1 or 2 dimensions? What if we have bosons or fermions? Can we identify genuinely quantum phase transitions? And would they also have something to do with kind of purity versus mixed? states, and the related question is that whether we also need to, if we are to consider mixed state, does it have to be some information theoretic kind of order parameter, or is it possible to even identify quantum phase transition in mixed states in these open-driven systems with conventional order parameters? And what can error correction what kind of role error correction can play in that context? Okay, let me stop there and take some questions, and then perhaps proceed.
So just to clarify, your definition of like quantum phase transition in these like driven distributive settings is that the universality class of the transition is the same as the like zero temperature undissipative point. Is that correct?
If I had that, I would have been very happy. So here in this context, I actually didn't look at the universal behavior. I mean, this is in the ground state. This is expected to be BKT. In this open-driven system, we don't have a handle on that. That's something I'm actually interested. So my definition, that's a very good question. So what's the quantum phase transition? So my definition is maybe a more loose definition here, is that almost any interesting phase transition that happens in one dimension has to be a quantum phase transition. But also in this case, it's not that we're kind of inventing this out of thin air. We have this spin boson model, which at zero temperature exhibits a phase transition. At any finite temperature, it doesn't show a phase transition. And now we have, instead of trying to cool down the system to zero temperature, we actually applied a bunch of dissipators. And it seems like the steadiest state, which was stabilized by the dissipation, exhibits a phase transition. So more likely than not, it has to be something more quantum. Now, whether that's quantum non-equilibrium or whether quantum equilibrium transition, that I don't know. Yeah, thanks for the question. Any other questions? Yeah. Yeah, so here this just this model also has kind of Ising flavor to it. So just by looking at the expectation value of the Ising order parameter, you can, identify the phase and the phase transition. Right. So in that sense, it's kind of it's something that's easy to observe and in something that's linear in the density matrix. No, that I'm not sure. I mean, I suspect that to be BKT, maybe a funny kind of BKT or more exotic kind of BKT, but what exactly the transition is, yeah. Okay, cool. I actually didn't really practice the next part, but I just keep it very short. I just, tell you a little bit about this, and this is mostly to inspire discussions maybe in the coming weeks. But basically the idea, as we heard in this workshop, is that noise and loss and decoherence should make life, easier and more simulable. So my main point, which hopefully I can make just in under 3 minutes, is that with dissipation you can actually find a kind of Monte Carlo for dynamics, which should make the system easy to simulate, at least if this dissipation is sufficiently large. Okay, the model that I'm going to consider is kind of a very generic model that you have in your quantum simulator of choice. This coupling doesn't have to be, this is kind of in the spirit of the spin boson model. You have sigma x coupled to that, but maybe you have something more like James Cumming. So that doesn't matter. The only thing that I want here is that you can have M bosons coupled to n spins, but bosons, when uncoupled, they just come with this quadratic part, and then the coupling is just linear in the bosonic fields, or let's call them cavity modes. And you have some dissipation acting on the cavity mode. It can depend on alpha or not, but that's up to you. So I want to make 2 claims. One is that you can trace out bosons exactly in a way that is general, is non-perturbative, but dynamics is still local in time. And that's kind of, that shouldn't really make sense to you, because often when we do this, actually in this talk, I already argued that when you integrate them out, you have this coupling in time. But there's a way you can trace it out and still everything, keep everything local in time. And second is that you can evolve each spin individually. So it's kind of a reduction of 4 to the n to 4 times n. Now, I know this seems too good to be true. It comes at the expense of sampling over unphysical states, but let me quickly go over this. So let's start simple. Let's say you have one bosonic mode, which is coupled to basically one spin. This is just a Rabi model. And the way it works is kind of I call it a hybrid, I don't know, quantum classical, stochastic approach. Okay, jargons are jargons, but basically what this means is that you replace the bosonic operator by a field, by a classical field, and make it subject to this equation. The simplest stochastic equation is linear and subject to white noise. It kind of seems like a semi-classical version of the cavity mode when it's not coupled to anything. And then take this field together with the white noise, which is responsible for this, put them in a field which I define as h of t. So this is, there's some element which is just proportional to the stochastic field plus I times noise. And then take this as a longitudinal field which is acting on this spin. And evolve your spin under this kind of fictitious dynamics. And then at the end of the day, just average over this noise. My claim is that this exactly reproduces the dynamics of the reduced density matrix of this spin. There's a catch. The catch is that this longitudinal field is actually complex valued. So your evolution is not entirely physical. Now let's consider a more complicated example. Maybe one cavity mode with some loss rate kappa. But let's say you have n spins in the cavity. Then by using the same trick, you can actually get rid of the cavity completely. So you can actually replace this by a bunch of spins which talk to some kind of a stochastic, a classical field. And then you can do more. You can actually decouple the spins, by introducing more noise fields. And this gives you a stochastic field for each spin that you just evolve on its own. And at the end of the day, you just average over this. And any correlations or entanglement that you have in the system would be generated only after you take the average over noise. On my last slide, this is just an example. I don't want to go into this. I just want to make the case that for some very large systems with dissipation, you can actually do some simulation. So this is the stuff that, okay, so this is the stuff that, yeah, okay. So far, everything I told you, including this, was in the paper that just published this year. But the thing that this is kind of more recent progress that you can actually show by using this stochastic equation, they also give you a different way of thinking about the dynamics. And in particular, you can show that if a certain ratio, if the ratio of the coupling divided by dissipation of the spin times the dissipation of the cavity mode, if this is smaller than some threshold, actually your dynamics is fully separable. This is something you can actually show. Even if that's not the case, meaning that if the interaction is larger or dissipation is smaller, it doesn't mean that you can simulate the dynamics. So you can handle some entanglement, maybe quite a bit of entanglement. It's very much work in progress. But it seems like that you're still capable of classically simulating the system, at least if these dissipations are not too small. That's the question?
Sorry, I'm just confused. So you're simulating each spin according to the independent noise? Like there's no correlation at all?
Yeah, sorry. I went over this so if you have many noise field, then if you have many noise field, then your field you still have the same field, but that field would be fed from sort of the sum of these noises which are acting on different spins. So there's a way that you can kind of correlate the dynamics of different spins are correlated. Yes. Okay, perfect. Let me stop here. I promise I'm going to keep it short. So let me not go any longer. I will just thank you, this gentlemen who have done a lot of heavy lifting, and thank you for your attention.
Great. Any more questions?
What limits are there on the Hamiltonian for the second part that you were talking about? Like, is it just exactly the Hamiltonian you were saying and nothing else, or can you like play with the coupling, or what?
Let's talk about the talk that we have a quantum phase transition. You're saying that is that
The part you just finished talking about.
Oh, the Hamiltonian. So I don't want spins to talk to each other. I want the spins only talk via bosons, and I want the coupling of the spin to boson to be linear, and that's it.
So
no other assumption.
I could have like exchange couplings, that would be fine.
Yeah, because that would couple. Oh, you mean at the level of the spin boson couple? Yes.
Yes.
Jane's coming? Yeah,
Yeah.
sure.
Okay.
Yep.
Thank you.
Yeah.
Yeah, so it's very surprising that you seem to get time local equations from integrating out those bosons. So normally that I think of that as the environment being Markovian, but that is that how you should think of this?
Yeah. So the trick is that if you just if I want to go back, I have to go back many slides, but this quantum classical mapping that you have the coupling between different spins, the spins are the only players in the game. So here there's also this field, and the field depends on the noise. The retardation in the system is encoded in this part of the system. So you have a quantum part which has spins. You have the classical part which can still encode retardation and this long-range kernels. So the trick is that to also keep track of that stochastic field. But life is easier because that's just a classical field.
I see. But so if you were to integrate out the classical field, then you would get.
If you were to integrate that, then you would generate a beast. Yes.
Makes sense. Thanks. Yeah. Any last questions? One more.
There's no limit on is there a limit on the strength of the loss? Like, does it need to be particularly large, particularly small?
So this is the stuff that I'm getting recently. I'm getting myself really excited about. But you can show that if you satisfy this. So I told you that the evolution is unphysical. So basically, what it means is that many of the good things are still there. The density matrix is Hermitian. Is trace fun. Well, you can enforce the trace fun. But positivity is the thing that you might sacrifice. So, and that's the only way that this could, because if I have kind of a mixture of, things which are also positive, I mean, this can't be the case. I also have entanglement. So you kind of manage that by allowing some redundancy in the system, and that you basically allow the density matrix for each noise trajectory to be non-positive. Now, if dissipation is still there, not zero, we can actually kind of put a bound on how large the violation of the blocosphere is. So maybe it's not exactly confined inside the blocosphere, but it would be a little bit larger. And that's controlled basically by how much dissipation you have in the system. Does that answer your question?
Yeah, so I'm trying to imagine the scenario where I extrapolate back to zero noise, right? Like, can I just replace all my exact diagonalization with the sampling stuff? Or how does it work?
So things really get bad if kappa goes to zero. Because that's kind of the trick that allows us to do a lot of things, is that, we have some, Markovian dissipation at the level of the bosons. But the spin going to zero, I think, again, I should emphasize that's work in progress, but seems like that's more manageable. Yeah.
Okay.
Yeah.
So sort of following up on that. So, as a Kavli QED person, that looks like cooperativity less than one, right? And so that should be the threshold sort of at which you no longer get decent spin-spin coupling via the photons, right? And as you go down from there, the photon dies too quickly for you to get reasonable spin-spin terms. Is that the right picture that I should, in the strong coupling limit, I would expect photon-mediated exchange between the spins to start cropping up. But this would, if I had to guess, this would be exactly the edge where I would say that process like stops being good.
So you have some intuition which is complementary to my intuition, but maybe something, and you might be right. One thing I would emphasize is that the effective coupling between the spins is also governed by the frequency of this cavity modes. And depending on whether that frequency is large or small compared to kappa, you can get different things. But you might be still right that this is not the most interesting regime. But I mean, to me, it's nice that you can actually put like a sharp bound on how large or small something has to be in order to, for the state to be classical. And also, if this is violated, you can still do things. But yeah, it's interesting that it kind of, this, which kind of comes out of the map, coincides with something that's kind of more physical. And I would like to learn that from you.
Yeah, like that would be the point that a cavity QED person would guess that I can drop the cavity and treat them as independent spins because they don't talk to each other via the cavity anymore. I mean, that's the boundary where this stops being a terrible idea.
I see. I would say they talk to each other, but they talk to each other in a way that don't generate entanglement. That's, but yeah.
All right, I guess we're just right on time. So this is the end of the conference then. Let's thank all the speakers and the organizers.
Thank you.